to new Cube video. I am your host, Pavel Savianko, and with this video we continue our series of short lectures about internals of Cube library. In previous videos I demonstrate you or explain you how the layout of Cube4 file looks like, basically the star. If you don't remember or you would like to recall it, take a look at here. And in this video I would demonstrate you or explain you how the one of the key files within this layout is constructed, so-called anchor.xml. And we will go then through the syntax, through the important parts of this file and what they mean and how one processes them. Okay, for that we start our nodes. Anchor.xml. So as a first node, one should say that there are two versions of Cube format, Cube3 and Cube4. Cube3 it is a legacy format, and this is purely complete XML file which consists out of the all definition of dimensions, of all metadata, and block with data in the end. In Cube4 we keep in XML form only the metadata definitions like descriptions of dimensions and so on, and the data is stored in a binary format separately. I will explain in this video Cube4 format. I will show shortly how Cube3 format differs to it, but I will not go into details. If you want to have details about it, please write in comments, and then maybe later I will create some video about it. So in this video only about Cube4, anchor.xml. Okay, so first of all, every Cube4 file .cubex consists of multiple files. One of it is anchor.xml, and that is pure XML file. So if you open it with the editor, you will find a typical structure of XML file with a starting tag and with all nested tags. These tags are of course defined by us, so the browser doesn't understand them, and we also do not provide so-called syntax check definition. It's only XML file, so one cannot display it basically. Okay, if one would like to know exact syntax of this XML file, one should better take a look at our parser generator in the source files. So syntax is defined in actually two files. In Cube4 scanner.ll, where our lexems are defined, and in Cube4 parser YY, where is actual grammar is defined. If one is familiar how it is constructed, it is best if you take a look at these files, and that is the final and the only correct source of the syntaxes of these files. Here I will show only general basic ideas which would allow you to understand how the file is constructed, but probably you will be not in position to create your own parser. For that you will have to study these files. I will display them in a minute. Okay, so the difference between Cube3 and Cube4, again, yeah, the Cube3 is only .xml file with extension of cube. It has a block with dimensions definitions and a block with the data, and cube4 it's anchor.xml plus binary data. Okay, and that is our point of interest. Okay, before I will show you actual grammar and example of XML file and how it is constructed, I will write you here shortly how the general structure looks like. So as every XML file, it starts with a tag XML and then goes version, this one, and then encoding, and then we have actually the main tag is cube, and it ends with dash slash cube, and it has different blocks. So one block is a general block which corresponds to the whole cube file. So I will mark it like this. So it is general block. Here are mirrors. Oops, what is that? No, I don't want it. No. Okay. It's mirrors, attributes, global attributes. Yeah, documentation, that is the mirrors and so on. And then we have the sequence section metrics, and it ends with metrics. Then we have a section which this section describes the list of metrics which are stored inside of cube file. Then we have a section which describes program dimension. It's program slash program. Then we have, of course, section which describes our HPC system. Slash system. And so at this moment, our anchor.xml in cube4 is over. So there is no further text anymore. There is a closing cube text is coming. If it is cube3 format, then we have here. Let me take a look. We have here severity section. I will show it also now in a minute. This section describes actual data which belongs to all these metrics and all these definitions. Okay, now let's take a look at actual examples. Here I will stop recording. Okay, so here I open cube file, so it is anchor.xml, and here is the example of this of such a typical file. And as we see here is it starts with XML tag, then the cube tag starts with the actual version of the syntax, and so in this case it's for the 4, and then we have that is this general sections where one has a list of attributes. These are global attributes. They for example, note the version of CubePL syntax, of the cube creating library, of the program actually which has been using this cube library to create this cube files, in this case that is Scorpii version 3.1. Then the aggregation modus, and we see that clustering is off. Clustering is example of such advanced topic. I will not go into it exactly in this video. I will explain it maybe later on within this series. But the clustering is controlled also via these attributes. There is no specific syntax elements are used. And then we see the section which describes documentation of the metrics. So where the documentation for every metric is actually stored is listed here in so-called mirror URL. It can be multiple of them, and for example CubeGUI goes one after another trying to find the documentation for some metric. Then we have the section of metrics, comes from here up to here, for example. Yeah, so these are approximately 11 metrics, and then description of every definition of every metric. It contains definition of every metric. Then in a section of region of program, it has a definition of every region being used in this measurement, and that's quite a list. And then actual definition of the call tree here, and call tree refers always to the region. So the regions are listed as a plain list, and the call tree is actually tree. So here is the ID of call path, and that is a region with ID 590. So one has to take a look. One of these IDs regions has ID 590, and so on. And by the end, one has a part which describes the actual system, where the system tree is described. And if one goes lower down, here is also topologies can be defined in these measurements. No topologies are stored, so it's empty, and then system is over and cube is over. That is the general structure of cube file with all these sections. So before I go a little bit into the details, I show you also the Flex and Bison files, where you find actual definition of the grammar of anchor.xml. So this is, for example, cube4 scanner.ll. You find it in source tree. So if you download cube library, some version tar.gx, you extract it, I go into directory crc, cube, gain crc, syntax, and here are two files, yy and ll. These files describe actual definition of or grammar of this anchor.xml. There are another yy and ll files, for example here in the CubePL directory. They describe the grammar of our derived metrics engine CubePL. About it there will be another separate videos. Here we are only looking at these two files. So let's take a look at ll. ll is a file which defines lexems. And if you are familiar with Flex, you will recognize here different sections. So like for example the header which will go then in generated parser. There are definitions. Here is the list of so-called contexts, and then is actually a definition of every lexem. Like for example here, this is this sequence of symbols in the context of attribute name leads to change of context, and it returns as a token this constant. So, and that goes on. You basically list all possible sequences of symbols in different contexts, and also switch of these contexts one after another, and for every of this token you return the constant. And the grammar is actually reacts exactly on this constant. So the grammar is described in YY file, that is the Bison file in this case. Again, we have here some header, definition of these tokens, like here error, plus, minus, dimension open, cube version, and so on, node open, system3 node open, and. So every basically possible token is described, also attributes which are possible in different tag. And then you start with our root rule. So this the grammar is defines the set of rules, and the definition is recursive. So for example, document consists out of two elements: XML tag, that is the very first one which I showed, and then cube tag. Cube tag consists out of the begin, content, and the closing tag, and the rule is defined usually. So once the grammar found or fulfilled all these rules, it executes this command. So in our case, it's only progress tracking. But for example, for executing rule cube begin, it has to go for this rule, and this rule is defined as opening cube file tag, and then depending which one will actually match. So there is a OR connection between them, so one of these rules will match. If out of some reason none of these rules or tokens are reported by the lexer, then the exception is thrown, and so on. So content consists out of 4 alternatives, so the attributes, docs, metrics, program, system, and severity text, different combination, and so on. That gives the flexibility in processing, but that's the way how this grammar is defined. And after, for example, after one after this parser read the attribute tag, it executes this piece of code. So in this way we construct our parser, and can actually then read in anchor.xml. In the further details, one would have to go already into source code, so we'll skip it. But if you would like to build your own parser of anchor.xml, it's the best if you just read this grammar, go through every rule, and then you will see how they are connected one with another. Simply because in actual example, not all cases are present. For example, like here, topologies are missing, and therefore by taking this example as a foundation for your parser, you will just miss it. Okay, let's go a little bit in detail. As you see, for example, attribute tag consists out of key and value. These are strings, obviously. The talk documentation tag consists out of one nested tag, mirrors, and mirrors has a list of mirror URLs. That's why MURL, and where the URL is as a content listed. This can be a local URL file or a remote HTTP or HTTPS. It has to be accessible then. And this is just a path being used to obtain documentation. So, and then let's take a look how the metrics are defined. Here is our metrics section, and here is example of a definition of a metric. This metric has a opening tag, metric, and its closing tag here. It has ID, 0, 1, 2, and so on. And every metric has a type, exclusive, inclusive, derived, post-derived, pre-derived, and so on. Which types are, I already explained in another video. What does it mean, inclusive and exclusive? So here it is a metric. It stores the values in exclusive manner. The another one, like time, is inclusive metric. And then we have subtags. For example, it's so-called display name. So that is the name of metric which is being displayed in a CubeGUI. It has this tag with its name, and then it has a unique name. Unique name is a name used to identify this metric internally by the library. So if you write some command line tools and you would like to work with some specific metrics, you use the unique name. Then data type, so unsigned integer 64 bits. Unit of measurement, so by visits it's occurrence, so called. It doesn't have seconds or kilograms, just occurrence, or how many times we entered the cube, some call path. URL defines exactly location of documentation of this metric. So in this case it is constructed like that. The mirror, that is the placeholder for the mirror URL for this one, and then the name of file and anchor within this file. So in history, if one goes from version to version of cube file, we might also develop syntax of first of all this anchor.xml, but moreover of the metrics, of performance metrics. Their definition might change from version to version of Scorpy, for example, if it is the generator of this measurement. Therefore, we store here the name of file with a version which describes exactly the metric which is being used by this version of Scorpy. So, and what Cube does, Cube actually takes this URL, replaces this placeholder with it, and creates the complete URL, and opens it like a normal HTML document, like we would do it in browser. And here is an anchor visit, so the browser will jump into the section of this document where the actual metric visits is described with probably some diagrams, some examples, and so on. And then there is a tag description. Here is just explanation, a short explanation about this metric. There are another tags are possible, like if it is derived metrics, there are expressions are defined to perform, how to do actually calculation or derivation of the values. There might be a formula or instructions how to calculate the actual values. And before closing this metric, another such metric can be defined as a sub-metric of it. Because it is XML file, the metrics can be nested one after another. In this case, we have unfortunately only plain structure of all metrics. They are all roots. They do not have children. Maybe I will open an example of cube file where it is as a tree. And that's all basically. That is how metric is defined. How the XML definition for derived metric looks like, I advise you to take a look at the flex and bison combination. You will understand definitely better. Okay, so if we go down to our program section is defined or consists out of two parts. So there is a plain list of regions. They all are listed one after another, because a region is a part of a source code. It can be re-entered multiple times, but that is the concrete part of the source code. That's why it has own definition with its file name and so on, and they're listed simply. So in this case, for example, region with ID 0, module unknown, not with unknown information about beginning line and ending line. So these are -1 and -1. That is such a so-called service region of measurement off. It means at that moment, it's virtually, we enter in a region where we switch off our measurement. So that's why this name is measurement off. The region names can have two forms, mangled or unmangled. The internally compiler works with a mangled name, and user sees then the human readable name. So we store both of them. Then we store paradigm. So there are, like for example, we see measurement, we see user, we see MPI, and so on. That is paradigm to which region belongs to, and then which role it plays within this paradigm. So for example, this role, this region is artificial. This role is atomic MPI. Here is all-to-all communication, and so on. Then there is a tag which describes documentation about this specific region. It's very rare, but some regions are they require special explanation, so they carry then the documentation URL in the same manner like it is with metrics, like where it is like this. So there is just documentation refers to another file which describes this or another region. And of course description, sometimes we put here also some lines which describe the region. So let's take a look, maybe there is somewhere lower. No, we don't have regions. So that is an example, for example, of region coming from OpenMP. The source code is given. That is the file where one finds the starting and ending lines. Obviously, it's a one-liner, and it is implicit barrier. It's coming from OpenMP, and it has a role implicit barrier. Yeah, that is which information is stored in description of region. And then at some moment, so once this list is over, the second section describes actually call tree, and this is not anymore plain region, that is actually tree, XML. So there is a C node, call path node, call node as you want, with ID. So it goes 0, 1, 2, 3, 4, 5, 6, 7. Usually, not always, but usually it is deep first enumeration, simply because when you execute a program, that's exactly how you experience the calls. They are created in the sequence. They are first encountered by Scorpio measurement system, and not to avoid redundancy, we simply store here reference to this region definition. It's defined only once as a region ID, and here we reuse it because one region can be called from multiple places, from multiple call passes. And we see that, for example, here one has a nesting. So this C node, before it closes, it has another C node with ID 1, with another region as a Kali, and this doesn't have anymore any nested call path. So um, in this way one creates the actual call tree. So the call tree consists out of all these references to different regions. And so the sequence goes. At some moment it's over and our call tree is constructed. And then we meet the section of anchor.xml, which describes system. And here is the grammar of system tree. The structure of system tree is a little bit special. It starts with a system tree node, and it has, of course, a name, class, because the nodes one can distinguish them. It might be the whole machine, some rack, some cabinet, and so on. So we write here machine, and on this level it can have hierarchical structure. So therefore it can have as a subnode another system tree node, and so this creates the tree like nesting. At some moment every system tree node, instead of having children or parallel to the children, can have so-called location group tag. So location group, it has also name, and location group corresponds to let's say executing unit, but not on like level of commands, of instructions. It's on the level of process, of program. So in this case that is the MPI program, so that is the rank 0 process. And because every process can have different threads, for example, or different streams or different things, then as a child of this location group is location. It has ID 0, 1, 2, and so on. It has also name, it has also rank and type. So type is thread, can be GPU thread, CPU thread, and so on. And that's all. So we have system tree nodes. They can be nested as they want, but at some moment they have to have a location group as a as a child, and location group has locations as a child. So there can be multiple location groups, and every location group can have multiple locations. And these locations, their ID, these IDs, they refer to the actual data. So if we speak about cube, we have 3 dimensions. So there is a data is constructed in the form of a cube, and these coordinates within this cube, as I explained already in previous videos, these are IDs of let's see, of metric, no, like this, here, metric, that is 1 coordinate, then C node, that's 2nd coordinate, and location ID. Location ID is the 3rd coordinate. Location group and system tree nodes, they do have ID, but they are used only to organize the locations, to have the relationship between these coordinates, but they do not refer to actual data within within data section. Only location ID refers to actual location of the data. About it I will explain, of course, in a video about location or layout of binary data. Yes, okay. So let's take a look at Cube 3 layout, how it differs. So let's take a look. That is the here. It starts the same with XML file. Oops, with XML tag. It starts with cube. Version is 3.0. Here is defined only attribute with the mirror for the definition of this matrix. In this case, that is this URL. It's obviously coming from old version of Scalasca software, from CubeGUI. Therefore, that's very ancient format. And then it goes in the same way like Cube 4. We actually developed Cube4 based on Cube3, of course, and therefore elements are taken over. And here is an example of nested metrics. So for example, metric time, before it closes, there is a definition of metric execution. So execution time, that is the actual execution plus idling. That would give the whole time which one gets built. But execution, that is the portion of time where actually calculation has happened. And then we see that this execution is also not closing, so it, as a submetric it defines MPI. So within the execution time there was a time which one has spent in MPI call, that would be then a MPI metric. And the metric MPI consists out of different times or calls, communication, synchronization, and so on and so on. So obviously in this example, all these metrics are having hierarchical structure, and that is exactly how it is defined here. So using this nesting property of every XML file. And then it goes in very same manner. Program section defines regions and call tree. So here are regions, and here is our call tree, also very nested, referring the region separately. Then we have system tree. Here one has to say that system tree grammar or definition has changed from Cube3 to Cube4. And Cube4 we have a little bit more advanced, more flexible grammar or definition of system tree. In the Cube3 it is very rigid, so there is a one level machine, that is this one, then always next level node, that is this one, then always next level process, and process has thread. And again, here is a coordinate for the data is thread ID. So process, node, and machine, these are organizational texts, they do not refer to actual data. But this tree is in Cube3 case always the same: machine, node, process, thread. In the case of Cube4, system tree node that can have as many children as it wants, system tree node, system tree node, system tree node, system tree node, as you want. Some of these system tree nodes can have location group, and location group, they have to have only locations as children, and these locations IDs, they refer to the actual data. So, and here for example we see that the system tree has a ID coming from 0, stop, here from 0 to, and then if you go to the end, to the 31, so we have 32 elements. Maximum that's 32 coordinates from 0 to 31 along the system tree dimension. And that is what we see here in a section which describes severity. We basically describe data for every of these coordinates. So first coordinate is a metric. So we see we have a matrix, and for this matrix consists out, or different matrices, they consist out of the planes, and every plane consists out of the rows. So so in this matrix, the one matrix with ID 0, that is our first metric, it was time. So, and we define the data for every C node. So from C node 0 ID for 1, 2, 3, as I explained for this coordinate, and we have here 32 elements, entries of data, which refers directly to these coordinates in system tree. So for every thread with ID 0, thread with ID 1, thread with ID 2, and so on. This is listed one after another. So, and then parser has to go then through it and then gather this data. In Cube4, this is not anymore the case. This data is stored in binary form. I will explain it again a little bit later. And but the very same coordinates are used to refer the data within this binary files. At this moment, I will remind you, subscribe, like, comment if you have some questions, or maybe you would like to have explanation of some aspect in deeper details. Yeah, that's it basically. I didn't explain you the actual structure for cube file when clustering is on, but that is advanced topic, and I will do it either later, or if you request especially, maybe then out of order. And also I didn't show you how the topologies are defined, but that is a good exercise. If you take a look in the file ll and yy, find their definition of topologies and go through these rules, and then you will see how topologies are defined. Spoiler alert, it's very easy. Okay. I hope you understood more or less how the anchor.xml is constructed, and again, subscribe, like, give us comment or questions, and see you next time.